So welcome back to Physics 105. This is Chapter 8, Equilibrium and Elasticity. So we're going to learn more about torque. We were introduced to that in Chapter 7. We'll do a lot more in Chapter 8. Solve problems of equilibrium of extended objects, balancing forces and torques. Use the position of the center of gravity and height to determine the relative stability of objects. Understand the nature of spring forces. Understand how spring-like restoring forces act during the stretching and compressing of rigid materials and biological materials, bones. So there you go. Okay, so a few weeks ago, we had equilibrium. Was this the sum of the forces were equal to 0? Well, now we have the ability to rotate things. So equilibrium means sum of the forces equals 0 and the sum of the torques equals 0. So the first thing we're going to do today is we're going to do some more torque problems. So everybody read that, please. So this is a realistic problem, you have to admit. I mean, how large can the mass of the sign be without breaking the cord? It seems to be a pretty reasonable thing. So, first of all, this is tough compared to the force diagrams. What's the object? What's the thing that's going to perhaps rotate? Well, it's the beam, right? Because the beam, gravity's pulling down on the beam, this is pulling down on the beam, this is pulling up on the beam. So the beam is the object. That's the first thing you have to figure out. And what are the forces acting on the beam? There's gravity, right? There's gravity, which we're going to draw at the center of mass. We have to be careful now. When you just had point particles, we just drew it, right? But when you have extended objects like a beam, you have to draw the weight at the center of the object, right? At the center of gravity. So we have the weight of the beam. We have the weight of the sign. Now, one thing. So technically, the tension, right? I mean, the tension is pulling down on the sign. However, the tension is equal to the weight of the sign. So we're just going to forget about tension. We're just going to say the weight of the sign. And we have normal forces. We have the rope. All sorts of good things. All right, so first off, draw the force diagram. Again, now you got to be careful. So here's the weight of the beam. This is a uniform beam, so the center of gravity is just at the center. Here's the weight of the sign. Here's this rope. Now look, okay, so here's a normal force, right? I mean, perpendicular to this. Now what's the deal with this thing? Well, I mean, think about it. This force would want to do, right? Wants to rotate it clockwise. Well, the fact that it doesn't rotate it clockwise means there has to be some vertical force there. Now, don't get upset because we're gonna solve this in a way where we don't care about that. So, don't worry about it. Okay. All right. Now, the way I approach these problems is I always do the torque equation first, and then, if I have to, I'll do the force equation. Sometimes you don't have to. Sometimes you can just finish it just using the torque equation. All right, so that's what we're going to do. Just going to do the torque equation. Now, when you're going to use torques, you have to figure out a rotation axis. And remember, you can put the rotation axis anywhere you want. So where you want to put it. And but you want to remember, torque equals the force times the lever arm. And so if you can put the lever arm, I mean, if you put the rotation axis at a place where the lever arm is 0, that's a good thing, right? All right, so where are we going to, can you cut it just for a minute? Thanks.